Hello, class. This is Mr. Hart. And this podcast, we want to continue our discussion of astronomy. And specifically today, we're going to talk a lot about stars. And we're also going to pick up on the history of where we left off. Last time, we talked about the history of the solar system with guys like Isaac Newton and Galileo. Today, we want to talk about the astronomy since then, and specifically of a very important astronomer named Edwin Hubble. Okay. Now, you may have heard this name because you know of the Hubble telescope that was named in his honor. It's a space telescope that kind of orbits around the Earth and takes pictures for us. Okay, but Edwin Hubble was an amazing astronomer. We could spend a whole class on just the things he discovered in his lifetime. But in the early 1900s or so, astronomy really started picking back up with people like Mr. Hubble and other astronomers like him. Okay. And one of the reasons why astronomy really took off at this point is because we were able to make better telescopes, okay, and things that could see much farther into space, okay. Now, there's two types of telescopes. I kind of mentioned them last time. There's the refracting telescope, which is a telescope that uses lenses, and this is the type of telescope you've probably seen, and it's the type that people like Galileo used, where they put a lens, and it's basically like a giant pair of glasses that you're using to focus light into a certain spot, okay. Now, these are pretty cheap to make. When I was a kid, you could even get them from like cereal boxes. If you send in enough box tops and things like that, you can get them for $5 for a really crappy one, or $50 for a nice one. But they're not the best telescopes because the resolution is usually pretty low, and they're really hard to scale. Making a really big lens is not easy to do. In the 1900s, they really started experimenting with reflecting telescopes. So reflecting telescopes use mirrors. So instead of going through a big lens, the light actually hits a giant concave mirror, which then reflects to an eyepiece mirror, which goes to your eye. And so you'll notice you actually look into the top of the telescope, not the bottom, like in a traditional type. But the nice thing about reflecting telescopes is you can make them really big, because it's hard to make a nice big piece of glass for a lens, but you can make a giant mirror by putting a bunch of little mirrors next to each other. Okay? And so if you see the big observatories, sometimes on college campuses or up on the mountainsides and stuff, they have reflecting telescopes. Just these giant telescopes with giant mirrors on the bottom of them. Okay? And so this allowed us to see much deeper into space. Okay? And that's when we started making more and more discoveries about the universe. Okay? And the people like Edwin Hubble were able to see much farther. Okay? So we're going to talk about stars mostly. Okay? And one of the things we started realizing about stars is where they come from. Okay, now you may have seen pictures like this on the right side. This is actually a very famous picture called the Pillars of Creation. And these are what we call nebula clouds. Okay, so a nebula is just a large cloud of dust or space material, basically just hydrogen and helium and stuff like that, that is gathering together because of its gravitational pull. Okay. Many stars will come from these giant nebulas, okay? Now keep in mind, this looks like a little small picture of something we're seeing in space, okay? They're 100 light years across, okay? That's this distance across, okay? So it would take light 100 years to cross that distance in the picture, okay? That is incredibly far away, okay? And that is an incredibly large amount of material, okay? So don't be deceived. It's really hard to understand scale in astronomy, okay, sometimes. But nebula is one of the things we started seeing and realizing that stars eventually come from this material. As it gathers and collects, it will come together and form stars, okay? Plus, one of my favorite things about nebulas is they just look cool, okay? You got the Crab Nebula, the Butterfly Nebula. They have cool names and stuff, and they just look cool in pictures. But again, they're just super large amounts of material waiting to gather together under gravitational pull and then start to make stars. Okay. So, big idea for us here is what we call Nebula Theory. Okay. All stars form from nebula material. Okay. Stars don't just appear. There's a gathering of the material together to form the star. Okay. And again, when I say material, it's nothing spooky. It's mostly just hydrogen, okay? Chemicals we know about that are coming together that will eventually form the star, okay? So we know where they come from, but why do they form from this, and where do they get their energy, and why do stars burn, and all this stuff? What's the mechanics, okay? So here's the idea, okay, with stars. Stars come from the fact that if you get enough pressure on things like hydrogen and helium, they will start to fuse together. Okay, this is called nuclear fusion. Okay, remember when we were in the energy unit, we talked about nuclear fission plants, where the material will break apart and release energy? Well, this is going the other way. We get things to come together, and that creates energy. Okay, so if you have a particle of hydrogen right here, okay, and a particle of hydrogen right here, and you throw them together really fast, they will actually merge together to form helium. Okay, and when they do that, they release energy in the process. Okay, so if you look at the inside of a star, what's happening is mostly hydrogen is fusing together to make helium. Now that process doesn't just happen, right? You need a lot of pressure, right? A lot of heat for this to occur, which is why nebula will gather hydrogen under gravitational pull for, millions and billions of years to get enough pressure on a single spot to start the fusion process. Okay? So gravity pulls that hydrogen in to the center. Hydrogen then fuses together to make helium, and the excess is released as heat, and that releases out the huge amount of heat that the sun gives out and light and all that stuff. Okay, it's the energy that comes from the nuclear fusion inside of the star. Okay, but that's all it is. If we could recreate this process on Earth, we would have unlimited energy basically for the rest of our lives. Unfortunately, we don't know how to do that yet because we need an extreme amount of pressures that we can't reach. Okay, but it creates a whole lot of energy. Okay, so let's talk about the different types of stars we see in the sky. Okay, so scientists actually are able to classify stars based on two things: their luminosity, or basically how much light they give off, and their temperature in Kelvin. Okay, so most stars kind of follow this pattern right here, where they give off a certain amount of light for this certain amount of heat that they have. For some reason, astronomers invert the scale, by the way. You'll notice that this is the hottest temperatures in the blue and the coldest temperatures are in red. So you'll see kind of this linear progression here, where most stars like to be in what we call the main sequence, where the hotter it is, the more light it gives off, and so on. Okay, our sun is a pretty standard main sequence star. Okay, it's about 6,000 Kelvin, and it gives off one sun luminosity by definition. But most average stars are somewhere in this main sequence. Okay. However, there are other common stars you'll see white dwarfs, which are stars usually when a star is basically dying off, where they're pretty dim compared to other stars at the same temperature, because they're losing a lot of their energy at this point and they're basically dying off. But you also get the supergiants, which are pretty cold, but they give off a lot of light because of how big they are. Okay, and so you can get certain supergiants that occur because of certain reasons, but usually it's just based on how much material the star had when it started to form. Okay, so basically we just classify based on how bright and how hot the star is. Okay, which usually is related to the size of the star. Okay. Last of all, let's talk about what happens to a star over its lifetime. Okay, so we call this the life cycle of a star. Now, we know from Nebula Theory that all stars start in a stellar nebula, gathering material. Now, just based on how much material they gather will change whether they go on the average star path or on the massive star path. Okay, if they gather an average amount of material, like our sun, they will burn as an average star for about 10 billion years or so. Okay, like our sun, it's about 5 billion years in on its 10 billion year life cycle, which is good. We got about 5 billion years left. And it'll burn that way for most of its life. Okay, they'll be kind of yellowish in color mostly. But when they start to die, what will happen is that they'll have to bring in more material, and they're not pushing out as much because they're running out of things to fuse. And then when that occurs, they actually get this big expansion called a red giant. Okay, so main sequence stars sometimes will go into a red giant and be a really large star that's not giving a lot of heat but gives off a lot of brightness, a lot of luminosity. Okay, then one day there's nothing left to burn, there's no more material to fuse together, and the star will just collapse, okay? And you'll get what's called a planetary nebula. Basically, all this material that it can't use anymore and can't hold on to will just kind of disperse, and you're left with a very small star called a white dwarf, which is basically not fusing anything anymore. It's just kind of the leftover heat from the star that was burning. Okay, so basically it's just a dead star that's still really hot and takes a long time to cool, and so it gives off light as it does so. Okay, so this is kind of the boring path of a star, and unfortunately our sun will do that. It's going to take the boring path, turn into a red giant, give off its material, and then kind of leave the burning core, okay, or the bright core, which is the white dwarf. Okay, let's go down the other path. So if you get a lot of material to start, you get the massive star, a lot of nebular material to start burning. You get these supermassive stars. Usually they burn a little bit brighter because they're a lot bigger and give off more energy. And then when they start to die, they also expand. And this is what we call a supergiant. A red supergiant usually is what we get. And same thing, when these things collapse, right, there's nothing left to burn, they'll collapse. But because there's so much energy in the collapse, they'll actually shoot out all that material in what we call a supernova. So you've probably heard of a supernova. Basically, it's an expansion or explosion of all the material that was left over from the supergiant that it doesn't need anymore. And in that process, because there's so much material on the inside of the star near the core, you can get a super dense star called a neutron star, or you can even get a black hole. And why this happens is there's so much material packed into such a small amount of space that you can even break down the electrical fields to where you only have neutrons sitting around in a super dense star like this, or you can get so much material that it actually rips a hole through the fabric of space. Okay, so this is much more interesting, and we'll talk more about these next time. Okay, but just understand that this is a very standard process. We've seen it throughout history, and we can see different stars in these different parts of the cycle. Okay, but that is the life of a star. So again, we know this all because of our increased ability to use instruments like telescopes and other measurements like that to learn more about our universe. Hopefully this all made sense. Go ahead and do your assignment on the life of stars. Let me know if you have any questions, and thank you for watching.